Welcome to Math, Minecraft, and Computers, episode I39. We're doing the 8-bit adder build in Minecraft. Recall that last time in LogicSim we created an 8-bit adder, actually by simply making 8 copies of a 1-bit adder, and used that to be able to do simple addition of two 8-bit binary numbers. Now you see the design here shows in the bottom left what we have, and we start with XOR gate. If you recall, XORs look like this in Minecraft. Then we need 2 inverters here, and there's lots of torches included. We need 2 on the top, 3 down here, and we need 1 here and 1 here to complete the inverters. Simply 2 pieces of wire between the inverters, wire there, on top of both of these blocks, and that is it. That should be an inverter. Now to test that, all we have to do is bring a couple of inputs in. And we can just use a torch. Let me put a light there so we can see. And now I want to put a torch here. You see our light comes on. That is one OR condition, so OR this input, and that's correct, but not both. And it goes out. So that is our XOR gate that we need in Minecraft. Now, as you see in our map, we need 2 of those. So I'm going to come off of this. I'm going to go 3 spots and then 1 over here and go 2 more. And then we're going to branch off of right here. And this is where we will need to eventually connect our OR gate through this area. So I'm going to stop right here, and this is going to be our second XOR gate. This will be the right input of the XOR gate that we need. So we do the same thing again. Coming off this one, you remember, is actually going to be our carry coming in. So for now, I'm just going to put a carry switch on this. That'll let us indicate whether we have a carry coming into this particular adder circuit or not. And that does our XORs. Now we come out of this same way, and we're going to put a riser here and a light here so we can see it from back there. And that is actually our data out. Okay, so this one serves as our data out. So if I come all the way back here, I'm going to put a couple of switches here too so I can control it. Oh, I'm missing my redstone right there. There it is. Okay. Now we're set. That is correct. So what should happen if I come back here, these are my 2 data bits, A and B. Let's say if either one of these is on, my light down there should come on. But if they're both on like this, the light should go out. Now, of course, the last thing that I have here is if I would have a carry on, that light should come back on. So we've got exactly what we want. If I didn't have any data and I had a carry, the light should be on. If I have 1 data and a carry, the light should be out. So this handles our data side of the circuit exactly. Okay, now that we have built our data path, this will handle the data line. Now we need to work on the carry line. And of course, if you look in our diagram here on the lower left, you can see what we need to do. First thing we need to do is move these back a little bit because we need a little bit of space here. So let's add some space there, because what we need to do is we need to connect this data line over here on the left side up and over a bridge, and that needs to go into a AND gate. So that AND gate will be positioned about right here, like so. And we also need this one coming into the AND gate too. So we'll put our switches right here. That can be our input. Of course, we've got our carry, and of course, this being an AND gate. We will need to put 2 torches on top and a torch here. And then just 1 chunk of wire there. We'll get this all wired up. Missed that. It goes here. There we go. Now we are connected. We have this AND gate, and we're going to come out of here with 1 piece of wire. So that is the AND gate here. That connects our 2 inputs and says if both of those are on, and only if they are on, then this gate will come on itself. Then if you recall, we actually have another one of those that come off the carry here. So we have to do the same thing with this line coming here and the carry. So let's move another bridge here. And we'll do the same thing. Our AND gate will be coming right here. It will come in on the input on this side. So once again, it's an AND gate. Get our torches going. Missed that. And our redstone wire comes out of here. Now I'm going to rewire this one up to this. And we are going to extend this here. So now what that shows you is that we now have, this gate will come on only when the carry is on and we have the data from here. That would indicate that we have 1 bit here and 1 bit here. And this back here would of course indicate that both of these are on, and so this would be off in that case. So that's what these are for. Now, if either of these conditions is met, that's when we actually have the OR gate for the output. So I'm going to bring these over to here. We're going to say if that condition, if either of these are on and that AND gate is on, or this one and that one is on and this AND gate is on, then we want to combine those into a OR gate. So I'm just going to tuck that OR gate in here a little bit, like so. We'll put it right here. And then it will come out. It can come out actually anywhere, but what we eventually want is we want that lined back up with it. So its output needs to come to here, which can be right there. Because this part here will of course connect to the other gate. Now, just to make a visual for this, we're going to put a lamp in here, like so. And I think I will put a repeater here just to make sure that we have enough power coming over to the next chunk. Now, to test this whole circuit, we should be able to, at this point, say, if either one of these is on, then both the AND gates are off. We have 1 data bit. If they're both off, everything is off. Now we have 2 here. What that will do is cause this flag to come on here and say that we actually have carry. Because those 2 bits added together actually mean our data is 0 and we have a carry over here. So that is all good. If for some reason we have a carry in from the last operation, then we just have 1 data there. As soon as I add one of these datas over here and input on this data side, then we move to the carry, and if I add the 3rd one, our data light should come on because that's 1 plus 1 plus 1 in binary, which is 3, which makes it 1, 1. And there you see it. Now we have completed our 1-bit adder. Now to make it an 8-bit adder, how are we going to do that? And you guessed it, we're going to copy it. So we're going to face, as a hint, with the sun to our left, so we are facing south. And then I'm going to pop up the homework, and you guys can figure this out on your own. And I'm going to give you just a quick, very fast look at what I did. Obviously, I'm going to show you the 2 blocks that I used that targeted the blocks. You can, if you want to and need to, you can slow this down and see what I did. But we've copied so many of these things by now, you should know exactly what to do. So this shouldn't have taken you very long, and I hope that you were able to get that on your own. Okay, so here's our circuit that we copied. There we have 1, 2, 3, 4, 5, 6, 7, and 8 of these. And you can see the way we copied them. The nice thing about it is they're automatically connected together. So our carry coming out of this one and into this one for every case is already done for us. So we have our inputs here. these inputs right here. So here is A1 and A and B1. This is A0 and B0 and so forth all the way down here to the end. There's going to be A7 and B7. So all we have to do really to test this is, and we'll put on 2 numbers. So let's just pick a couple of numbers and see what we come up with. So ready to test. Remember, this is the only carry, so this would be the carry flag coming in. And then even though it's going to light these up, they actually don't count for our output. Our output of the addition is going to be here, and the final output of the carry is going to be here. So I think I want to elevate this one up to make it easier to see. Okay, now you'll recall that this is a ripple circuit, so the data ripples from this side to this side. That means that our low order bits are here, and the high order bits are down there. So when we put on our values for a number, we actually have to do them in right to left instead of left to right. So this becomes a 1. 1. Then we skip, we're going to leave that as 0. We put another 1 here, another 1 here. We skip and we put a 1 on here, like this. That is our A value that we have here on the screen. It's time to put on our B value, once again going from right to left. So here we go, starting with 2. We have 3 ones in a row. That's 1, 1, 1. We then skip. That's a 0. We turn on this one. That's a 1. We then skip again and turn on this one for a 1 here. All right, now we should check and see what value we get. Once again, going right to left. Looks like on all of these circuits aren't lined up. Looks like we need to add 1 chunk of redstone to all of these. Okay, now that we have solved all of the bugs, we should be able to check our result. The result from right to left should be 0, and then a 1, and then 2 zeros, and then 2 1s, and then a 0, and then our last bit down there is on, and carry is off. Now, of course, if I turn either of these switches on, right here, to add 1 more bit, you can see then that that would go off, and we would end up with a carry over here. And so, this is how our adder circuit works. Now that you have this, you can put whatever values you want on this. You can see if it works, add them up. But this is actually now an 8-bit adder. So that is I39. Next time, we're going to build what is a counter, which will be very interesting. We're going to look at actually counting in binary and see what that looks like. And we're going to build a counter that will do that both Logisim and Minecraft for our I40 episode. We'll see you then. Hope you learned something. Keep on learning. Give me some likes with the thumbs and subscribe if you want more. This is M. Roy with I39 out.